Okay, so let's continue. And here we'll talk about the matter wave. So it's not only photon has the duality, both the particle property and the wave property. We also have the matter wave. All the matter can be as a wave. So in yesterday I mentioned that in 1916 Einstein proposed that for the photon it should have a wavelength as h over p, or p equals h over lambda. So Einstein proposed that only for the photon, but later on, this one called the de Broglie, I'm not sure how whether I pronounce it correct, but yes, it's a de Broglie in his PhD thesis proposed that all the matter should also satisfy this equation. So de Broglie suggests that P equals h lambda might apply not only to photons but also to electrons, and of course even for other material. But if your mass is too large, then your de Broglie wavelength will be very short to observe. So actually, de Broglie called this one the de Broglie wavelength. And yeah, this is the experiment to verify this assumption, because in so for this experiment is called the diffraction, so that you will see many rings there. So there's an incident beam, X-ray, or electron. Actually in 18th or 19th century, they already has this experiment for the light, and then shoot on some target aluminum crystals, and then there will be some pattern, something like this side is lighter and the other side is darker, which is farther away from the center. So actually, this is still a Fourier transform. It is like the same function, yeah, which is like that. So close to the center, it is larger, and then farther away from the center, it becomes smaller and smaller for every peak. Okay, so this is the diffraction technique. But yeah, maybe 100 or 200 years ago, they already have the experiment for the light, or for the EM wave. But actually, 100 or 200 years later, they find the electron also have the same phenomenon. So this one is for this is figure B, is for the X-wave beam, light wave. We have the pattern like this. And for the C is the electron beam, the matter wave. The electron also will have the interference with itself, actually the diffraction with itself. So note that two patterns are geometrically identical to each other, although you feel like, oh, this is darker for C, and then a bit whiter for this one. But actually the pattern are identical. So this is one of the experiments to show that the matter also will act like a wave. And if I remember correctly, like 3 years ago when I teach this course, then there is an experiment in America using some biomedical molecule, something like the protein, 用一些蛋白质的分子去做这个实验， and then they still find that the protein molecule can have this kind of phenomenon. Okay, so let's see a sample problem here. So what is the de Broglie wavelength of an electron with a kinetic energy of 120 eV? Okay, so actually we will use K. So in classical mechanics, we will use 1/2 mv squared, but in quantum mechanics, we usually use p squared over 2m rather than that, because p equals mv, so p squared equals m squared v squared, so cancel one of the m, so actually these two are the same. So yeah, usually we'll use p squared over 2m. Okay, so then we could have p equals square root of 2mk. So you just move 2m over and then square root on both sides. So this is 2 times for electron. The mass is 9.11 times 10 to minus 31. And then k is 120 times 1.6 times 10 to minus 19. Okay, yeah, so this is 5.91 times 10 to minus 24 kg m per second. Okay, so the de Broglie wavelength is nothing but lambda equals h over p. P equals h over lambda, so lambda equals h over p. So this is 6.63 times 10 to minus 34 over 5.91 times 10 to minus 24. So this wavelength is around 112 picometer. Picometer is something that we can still observe. Is something that we can still observe. You can imagine if this is p. This is p. If you consider ourselves have a much larger mass, so there will be a large momentum. In that case, the wavelength for a much larger particle will be much shorter to observe. So actually, the easiest way to observe the matter wave is using the electron, because it's almost the lightest particle. Yeah. Okay, so here we come to the most difficult part, which is called the Sorensen equation. So it says if a wave function psi x, y, z, t. So we have 3 position coordinate and 1 time coordinate can be used to describe the matter wave. That is space-time variable can be grouped separately and can be written in the form. So it's something like the separable of variable we introduced in supplementary note of chapter 33. So yeah, if the potential field for the particle is not time varying, then we can usually separate the time function out here. And here, omega is the 2 pi f is the angular frequency of the matter wave. Okay, so if you still remember in chapter 31 when we try to solve the wave equation, we get the solution to be something like Ex equals E0 cosine kx minus omega t. If we write it in a complex form, it will be like the real part of E0 exponential to j kx minus omega t, like this, or I. So we will distribute this one into here, so you will get exponential to minus j omega t, exponential to minus I omega t. So this one might be something like exponential to jkx, something like that, something like that. And this will be the most proper, most easiest solution for the Sorensen equation. And actually, this inspires us to sell out the Sorensen equation. Really makes sense. It's something like we have the solution first, and then we try to write out the original differential equation to get that solution, and then after making some other assumption, then we can able to find some more interesting property due to the Sorensen equation. So this is strange. Usually when we see a problem, we try to write an equation and then try to solve it, and then to see whether the solution give you some interesting interpretation for the phenomenon. But actually, the Sorensen equation is somehow like you first imagine the solution will be look like just like a plane wave, and then you try to imagine what makes the equation make sense. Something like kinetic energy plus the potential energy would be the total energy, and then using some classical mechanics interpretation, and then you try to write out the Sorensen equation, and then it turns out that Sorensen equation makes sense. It gives some precise prediction for the phenomenon. Okay, so here, suppose that a matter wave, which is a particle detector, then the probability that the particle will detect a specific time interval is proportional to this one. Just mentioned previously before, this is the Copenhagen interpretation. So phi is the solution for the Sorensen equation, but it doesn't have any physical meanings. The Copenhagen interpretation is that you take the absolute value for the wave function and then take the square. It becomes the probability density function. It becomes the probability density function governing the particle. So yeah, where is the absolute value of the wave function at the location detector? Okay, so this is always both real and positive, because you take the absolute value, even though the wave function could be complex function, and usually a complex function. But after you taking the absolute value, it becomes real function, and then taking this even without taking the square, taking the absolute value of a function will always be positive and real. So it's called the probability density function. So the probability density function of the detector, blah blah blah, center point is proportional to the value here. So this is the Copenhagen interpretation. And here it mentioned the Sorensen equation. Actually, so matter waves are described by Sorensen equation. Suppose a particle traveling in the x direction through a region in which a force acting on a particle causing it to have a potential energy ux. So of course the field can have a potential energy or potential field to make things moving in some specific way. So in this specific case, Sorensen equation can be written as this one. Oh, it looks so complicated. Actually, I will not try to tell you why at this moment. After finishing the slide of this chapter, I will try to tell you a derivation of this Sorensen equation. Although it will still look complicated. But yeah, actually just try to accept the Sorensen equation look like this at this moment. Okay, so this phi is of course the position part, of the wave equation. Of course, now we all in this course we will all the way assume the potential field is a constant, so that we can always isolate this term out. So this wave function is nothing to do with the time. It only related to the position. So this is a wave function only related to the position. So this is the second derivative of it. Something like the wave equation. If you still remember, the wave equation is like Laplacian of something, maybe E equals partial t. Sorry, not partial t, partial E. Partial t square, and then 1 over c square. If you still remember, this is the wave function. And actually this is the second derivative with respect to x in one dimension. So which is like this term, but actually this term is not like this one. Okay, so here we have another term. So we have something like the constant. 8 is a constant, pi is a constant, m is the mass of the particle. So for a specific particle, it is a constant. This is a Planck constant, of course. So we have this term multiplied by this one. E is the energy. E is the energy. Usually refer to the kinetic energy of the particle. Although this is using E, and also chapter 37 we also use E, but in chapter 37 we use E for the total energy, including the rest mass. So don't try to get mixed of it. So this E usually refer to the kinetic energy here. So E is the energy of the particle minus the potential. Of course, it does not related to time. It does not change over time, but it can be related to the x, to the position. So here we have the residual energy, just something like your particle has some energy, and then some of the energy is consumed by the potential energy. So this is the residual part, multiplied by this constant, and then multiplied by this phi. So this is something like a second order differential equation. And actually, before I have mentioned that usually only using Planck constant to write the equation will look more complicated. If you use h bar, the equation will look a bit more elegant. So if you still remember, h bar is h over 2 pi. So here, h bar square is h square over 4 pi square. So here we have 8 pi square, h square. So we have h bar square here, and then we still have another factor of 2. 2 times 4 is 8. So we have 2m over h bar square. So this term look a bit more elegant than this one. Don't have the pi square there. Okay, so sometimes we will just write it like this. Okay, so for a free particle, so here we try to solve this Sorensen equation for the most easiest way, which is the free particle. Just like we try to solve the Maxwell equation, for the easiest way is the EM wave in free space, which means there are no charge, no current in the space, and then the wave will look like a plane wave. So we will also expect there will be a plane wave for the Sorensen equation for a free particle. So which means that for free particle, we don't have any potential. Potential is something like if you have a potential like this, and then you put a ball here, then the ball, if there's no loss in between, then the ball will roll like this, go to here, and then going back and forth, so on and so forth. So this is so-called the potential field. So here, if we don't have any potential field, which means that this u of x is nothing but zero. And then equation describe a free particle where the moving particle on which no net force acting on it. The particle total energy in this case is all kinetic. And the energy becomes this one. So as this is kinetic energy, it is 1/2 mv squared. We don't consider the relativistic effect here. We don't use the gamma minus 1 times mc squared. Here we don't consider the relativistic effect here, so we only use the classical kinetic energy here to substitute the total energy E. So after substituting the term here, we can do some cancellation or simplification. So in this case, these two and this 8 can be partly cancelled, and then we can group some of the term. So we have 4 pi square. So it is like 2 pi quantity square, and then later on we have m square. This is a m, this is another m, so we have m square v square over h square. So mv is p, so this is p over this is not h bar, this is h, p over h quantity square, p over h. P over h is P over h here. P over h is actually 1 over lambda. P over h is actually 1 over lambda. So this is 2 pi over lambda. So this is nothing but k. So for the free particle, the Sorensen equation becomes this form. This is a second order constant coefficient ODE. So you know the solution for this one will be nothing but if you still remember, you can write the solution to be like a cosine kx plus b sine kx. But actually here we don't try to write it like this, we try to write it as a complex function. But if you still remember how do we find the solution, it is like this is a second derivative, we change it to s square and then plus k square, and then this is the original function, so this is nothing but 1, so equals 0, and then we will get s equals plus or minus j times k, and then originally how could we come out with it is that we assume that phi equals exponential to st, so s equals to plus or minus jk, which means that phi will be a times exponential to jkx plus b times exponential to minus jkx. See, this one comes out exponential to jkx. If you multiply it back here, then you will get this. Exponential to j times kx minus omega t. Okay, so here we can observe, this is actually the plane wave. But of course a complex function. And actually we need the complex function for the Sorensen equation. If you limit the solution to be real, then it will not give you interesting result. So in this case, if we assume this is free particle, we will get this. We will simplify the Sorensen equation to be this way, and then the solution of it will be like this. Phi of x equals a times ikx or jkx is same. I and j are also square root of -1, and then plus b times minus kx. So if you just multiply back, so this is the big phi, which is phi times exponential to minus j omega t. So it becomes a times exponential to j kx minus omega t, and then plus b exponential to minus j kx plus omega t. So this one is propagating in the positive x-axis. This one is propagating in the negative x-axis. So sometimes we only just pick one of them is already okay. But generally it can be both positive and negative. And of course a and b are also complex constant. Okay, so we have mentioned that actually the wave function doesn't really have physical meanings, and so far the only physical meaning we know is the probability density function. Then we need to take the absolute value of the wave function and then take the square. So let's say this is the wave function we just solved, and then for simplicity we only consider the positive one. This is propagating in the positive x-axis, because it can either propagate in positive x-axis or negative x-axis. But yeah, so for simplicity we only consider the positive one. So this is the wave function we try to solve. And so let's try to take the absolute value. Take the absolute value and then take the square. And then we substitute this one into here. And phi 0. Yeah, we also assume that phi 0 is nothing but a real value. So it just come out. If it is still a complex number, it doesn't really matter. It's just like a phi 0 square. So it doesn't really matter here. And then of course, this is like absolute value of a times b square is absolute value of a square times absolute value of b square. So this one comes out, this one is like this. So actually, you know the Euler's identity, which is like cosine ikx is exponential to ikx is a cosine kx plus j sine of kx. So you take the absolute value will be like this one square plus this one square, and then take the square root, and then you take the square again. So it becomes cosine square plus sine square, which is nothing but 1. So this one is 1. So and then you see that this is the probability density function of the free particle, which is like a uniform function. This is uniform over the x-axis. Because it is free, you don't really know where it is. It is free. It can go everywhere. For every moment, you don't know where it is. It is just equally probable over the space. You can never find it. So here, it inspires something like the Heisenberg uncertainty principle, because for free particle, here the probability density function is like, oh, you cannot see where it is actually is. It's somehow like equally probably in the whole space. Actually, we cannot know where it's at a specific moment. And the Heisenberg's uncertainty principle is like this. We have a delta x, which means that if we try to measure the distance, the position, the x coordinate. Yeah, all these three are just x, y, z coordinates, so you can just clear the first one. So delta x is the x coordinate. If we try to measure it, there may be a measurement error. This measurement error, we call it the delta x. And also, we try to measure the velocity or the momentum. Of course, if we know the particle, the mass of the particle, if we know the velocity, we know the mass, we know the momentum. So it says, if we try to measure the position and also the velocity or the momentum, there will also be error. The error for the position is delta x, the error for the momentum is delta p in x-axis. And these two errors the product of these two errors are always larger than this h bar, are always larger than this h bar. Which means that if you try to measure the position very accurately, then you will have a very, very large error for the velocity, and vice versa. And if you try to keep both small, then there may be a small value for both of them, but the product of them must be larger than h bar. Or more rigorously, 更严格的说we'll use this sigma x, which is the standard deviation, 标准差, to describe the error, because if you just do it once, then it might not make much sense. So this is so-called the standard deviation of the position difference or position error, and the standard deviation of the momentum error. The product of them is larger than h bar over 2. Actually, when Heisenberg tried to propose this uncertainty principle, he proved it for the normal distribution only, but actually it will be applied for any of the wave function. So Heisenberg uncertainty principle states that the measured value cannot be assigned to position and the momentum of the particle simultaneously with unlimited precision. You cannot measure both of them precisely at the same time. If you make one very precise, then the other one will have a large error. Or sometimes we will interpret the Heisenberg uncertainty principle like if we try to measure it, then we will make it change. We will make it change. Because if you try to observe a particle, the position of the particle, you probably need to use some light to observe the particle. Then when the light hit the particle, then there will be some energy transfer to the particle, then its position or the velocity will change at the same time. So you can never measure the position and the velocity of a particle precisely at the same time. Okay, so here this delta represents the intrinsic uncertainty in the measurement. So even with the best measuring instrument, each product of a position uncertainty and the momentum uncertainty will be greater than h bar. So let's see an example. For free particle, we have phi x to be exponential to I kx. We just find this solution. Maybe yeah, I can also put the phi 0 here, like this, phi 0 here. Okay, so just now we already derived that. This is the probability. This is the probability. Maybe we can call it a P of x. P of x is nothing but phi 0 square. Phi 0 square. Which means that this is the P of x, and then this is x-axis. This is phi 0 square, which means that the delta x tends to infinity. Delta x tends to infinity. The error is really large. The error is really large because this is equally distributed over the space, over the x-axis. And even though you have a delta p equals 0, delta p equals 0, then yeah, of course you have something called a indeterminate form. And of course, P equals h bar k. If you still remember, P equals h over lambda, and then if we have h over 2 pi and then 2 pi over lambda, so this is h bar k, which means that delta p equals h bar times delta k, and then delta equals 0. So which means that delta k is 0, because we actually have a fixed k. The k is fixed. We only have a single wave number. The frequency is very precise. The wavelength is very precise, which means the wave number is really precise. We have delta k equals 0, which means that delta p is also 0. But in that case, infinity multiplied by 0, which is still larger than h bar over 2. But here, if we imagine if delta k is slightly larger than 0, which means that in the k domain, it is not a delta function anymore. It is something like this. Or actually, if actually it is like a delta function. Also, this is also a wave function in the k domain. Between this and this, they are related by the Fourier transform also. Because when you learn the law and system, you know for a constant function, if you have a maybe xt equals delta t, then you take the Fourier transform of xt, it becomes 1 in the frequency domain. And vice versa. If you take the Fourier transform of a constant function in the frequency domain, it becomes a delta function. Of course, you multiply by factors, 1 over 2 pi, something like that. But actually, that's the case, or 2 pi. So actually, this is something like the Fourier transform pair in the x domain and the k domain. And for the next case is the normal distributed wave function. Actually, when Heisenberg proposed the Heisenberg uncertainty principle Actually, he proved these cases. So suppose we have the phi k to be a normal distributed function, which is like a 1 over 2 pi sigma k, and then times exponential to minus k0 square over 2 sigma k square. So this is a normal distribution. If you take the absolute value and then take the absolute value of it and then take the square, it is actually still the normal distribution, which is like this is 2 pi and then sigma k square and then exponential to minus this one square will be like k minus k0 times 2 and then 2 maybe 2 and 2 will just cancel each other. It looks like this because if this one take the square, it just multiply 2 to the exponent. So when you take the absolute value and the square of it, it's just like this. Okay, so in the x domain, it is nothing but the Fourier transform of this phi k, and actually which is like 1 over square root of 2 pi, and then from negative infinity to infinity, and then we have a 1 over square root of 2 pi sigma k, and then exponential to minus k minus k0 square 2 sigma k square, and then exponential to minus ikx dx. You may ask why I put 1 over square root of 2 pi here. It is just for normalizing the Fourier transform and inverse Fourier transform. For different textbook, it has a different definition for Fourier transform. Sometimes it put all the ways 1 over square root of 2 pi for both Fourier transform and inverse Fourier transform. Then, but for the signal and system textbook, you use 1 for the forward Fourier transform, and the inverse Fourier transform you have a 1 over 2 pi. And for some of the textbook, it use f, so that it don't have a 2 pi factor there. So it depends on different textbook has different definition. But here I just use 1 over 2 pi because this is a probability density function like function, so it should be normalized. We're better for that. And of course we can just simply do some variable change of variable, do substitution, something like k prime equals k minus k0. So it will look like 1 over square root of 2 pi, and then negative infinity to infinity, and then we have 1 over square root of 2 pi sigma k, and then exponential to minus k prime square over 2 sigma k square, and then exponential to minus I k prime x d k prime. So how to calculate this integral is that we could complete the square here. So we will have 1 over square root of 2 pi, and then here's integration of from negative infinity to infinity. We have 1 over square root of 2 pi sigma k, and then exponential to negative k prime over square root of 2 sigma k quantity square plus 2 times k prime over square root of 2 sigma k, and then times this one is I sigma k x, and then square root of 2, like this. So this will look like the original one, because we have square root of 2 square root of 2, it becomes 2, and then cancel with this 2, and then this sigma k and this sigma k will cancel. It turns out to be I k prime x, of course with a negative sign in the front, and then we complete the square like I sigma k x over square root of 2, and then square, and then plus I sigma k x square over square root of 2, something like this, and then dk prime, like this. We complete the square of this exponential function. This is nothing but a constant, so this is not so difficult. Okay, so the next step is like it is equal to 1 over 2 pi sigma k, and then integration from negative infinity to infinity, and then we have exponential to negative k prime minus square root of 2 sigma k, and then plus I sigma k x over square root of 2. So this term square, and then another term is exponential to negative sigma k square x square over 2 dk prime. So this is not related to k prime, which means that we can just put it in the front, and then this is nothing but exponential function, but it is square. So to finish this so-called the Gaussian integration, Gaussian integral, we still have some path to go. And of course we need to use a u substitution first to make things look more easy. So let's take u equals this term, which is like k prime over square root of 2 sigma k plus I sigma kx over square root of 2. So we let u to be this one. So this one becomes exponential to negative u squared. So it looks nicer. Yeah. Du equals, so taking the derivative of it will become 1 over square root of 2 sigma k dk prime. So this one, phi x equals 1 over square root of 2 pi, and then exponential to this one. This one, we move it to the front, so it becomes negative sigma k square x square over 2. And then the integration becomes negative infinity to infinity, exponential to negative u square du. I'm not sure whether you in the calculus class you have learned how to do this integration. Actually, if the limit is not from negative infinity to infinity, or from 0 to infinity, it might not be integrable. There is not closed form for the indefinite integral. Only the definite integral from negative infinity to infinity, or 0 to infinity, or maybe negative infinity to 0 can be calculated. And actually this one is nothing but a square root of pi. Square root of pi. You can do it. Yeah, you can check it. The way for doing this is like if you assume I equals integration of negative infinity to infinity, exponential to minus. Maybe we can just put it like x squared dx, because this is just a dummy variable for the definite integral, so it doesn't really matter. And you can try to calculate I squared equals integration of negative infinity to infinity, exponential to negative x squared dx, multiplied by integration of for the same boundary, and then exponential to negative y squared dy, and then we can merge these two together. So we have a negative infinity to infinity, negative to infinity to infinity, and then exponential to negative x squared plus y squared dx dy. And then you can use some change of variable, like change the Cartesian coordinate to polar coordinate. So which is like r equals square root of x squared plus y squared, and then theta equals arctangent y over x. So this integral will become 0 to infinity, because r is non-negative, and then theta is from 0 to 2 pi, from 0 to 2 pi. This one becomes exponential to negative r squared. Dx dy will become r d theta, if you still remember. Changing from the Cartesian coordinate to a polar coordinate, dx dy becomes r d theta. So this one, we can calculate this easily, because r dr is nothing but 1/2 dr squared, 1/2 dr squared. So this is r squared. We can calculate this easily, because or maybe I should reverse it. This is d theta, this is dr. So it will become 0 to infinity, exponential to negative r squared d times r dr, and then 0 to 2 pi d theta. So this is nothing but 2 pi. This is 1/2. And then we finally find that I squared is pi. I squared is pi. So this integration is square root of pi. So finally, we can see that this is square root of pi. This is square root of pi. And then you can see that phi x is nothing but 1 over square root of 2 pi exponential to negative sigma k square x square over 2. Like this. Like this. And yeah, referring back to here. Referring back to here, we have this one, phi k square. Phi k square is something like something times exponential to negative k minus k0 square over sigma k square, like this. And here, if you take the absolute value and then square of this term, actually I missed something here. It should be something like sigma k square like this here, but I'm not. Yeah, maybe I missed something before, but it doesn't really matter here. If you really need a correct calculation, then you can check back where did I miss the term. But here, if you take the absolute value of this one and then take the square, you will have so we have a constant term here, and then exponential to minus sigma k square x square not over 2, because these 2 cancel with these 2. In that case, this is the standard deviation will be like something exponential to minus k minus k0 squared, and then this is 2 times sigma k over square root of 2 squared, and then here it is like something exponential to negative x squared 2, and then 2 sigma k square root of 2 sigma k square. Okay, this square root of 2 square, and then cancel with this 2, and then this sigma k square going up like this. So this is the standard deviation of the x, and this is the standard deviation. This is the standard deviation of the k. So this is delta k, or sigma k. Maybe I stop here today. It is already 50, so let me stop here today. Maybe we continue next week, November 17.